So we're going to start today and talk about a sort of higher level overview of some of the concepts that we've been covering in some of the past classes, and sort of generalizing everything into a framework that hopefully makes some of this, some of the ideas that we've been talking about a little bit more unified and digestible. So we'll start off talking about generalized linear models, also known as GLM. So this is a class of models that can be generalized across a set of specific characteristics. And those characteristics are: one, a random component, a systematic component, and three, a link function, which we'll characterize like so, which describe how components relate. So what I want to do now is to think about previous examples of models and how they can be characterized. So previous examples of models. And the first one is kind of the most basic one that we've talked about for a while. So linear regression. So we've got yi equals beta naught plus beta 1 xi plus epsilon I. So the random component is this term here, which is our error term. And in this one, so hopefully everyone's familiar with this at this point. So we assume errors are normally distributed. With n 0 sigma squared. Our systematic component is this entire term here. And this is linear in parameters. So our function looks something like this. If you have it in matrix form. and our link function is an identity. Okay, so this is kind of the basic structure of if we were to put this into the context of a generalized linear model for linear regression, it's defined by essentially these three components that look something like this. And the sort of beauty of the GLM is that this concept can be applied to a whole class of different regression models. So we can look at another example of one that we've done. So logistic regression. So that looks something like this, logit pi, right, where this is the probability of success. It's equal to log of pi over, 1 minus pi, which is equal to beta naught plus beta xi for each of your choices, k. In this case, our random components distribution of y is binomial, n comma pi. Our systematic components is linear. Oop, I should be using a different color. Hang on. So this is linear in parameters, right? We can see that here. It's all linear. And lastly, our link function it is a logit link, right? We have something like ln so again, with these three basic components, you are essentially able to generalize any linear model into some kind of characterization that can be described with these components and link functions. And there's a whole class of other regression models that we haven't talked about that can be put into this framework. So other regressions. So for folks who want to kind of explore the more statistics-oriented regression components of a GLM, this will be hopefully somewhat useful. So we've got our random component. Systematic components. And a link function. So what are some other model types? You got log linear. The random component here is a Poisson distribution. Because we're doing GLMs, actually everything is going to be linear. And the link function is a log where x beta is equal to ln of mu. There's Poisson. This is also looks similar. You can have an exponential random components. It's a negative inverse. Inverse Gaussian. Okay, so these are just a couple examples of possible GLM models that we're not going to cover. But this is hopefully just to provide a little bit of context for folks to get some understanding that the GLM itself is kind of this useful structural tool where you can apply lots of different transformations to random components and to the link function to run regression models of a specific type if the sort of context of the analysis that you're doing, requires you to have, some kind of transformation like this. Okay, I see a question. So the random component is Y in the logistic regression. Okay, in the logistic, it is the distribution of Y, which is binomial. So usually the random component of the GLM is referencing some distribution of your outcome variable. So in the linear regression, right, it's a normal distribution based off of the error term. In the logistic regression, it is the distribution of your outcome choices. So we can say in a linear, it's normally distributed. In logistic regression, with two outcomes, you have a binomial distribution. hopefully that's answers your question. Great. Okay, any other questions about this? This part is mainly conceptual, like we're not actually gonna run any code or anything. This is just kind of providing a framework for folks. Yeah, and usually it's a sort of nice little framework to get organized conceptually about the sort of relationship between different linear models. Okay, so that is kind of the first bit of stuff I wanted to cover. The second half today, or I shouldn't even say second half, second portion. So as we've been moving towards more sort of predictive methods that are more in line with kind of machine learning approaches, we've looked at some of the analogs for a linear regression through doing things like splines. There are sort of similar analogs for doing classification. So today, the main thing we'll be talking about is sort of an analogous application of sort of early machine learning tools as applied to sort of classification problems. So let's talk about this. A hyperplane is a flat affine subspace of, oops, what the heck did I just do? Of dimension p minus 1 in p dimensional space. Okay. Complex definition for a fairly straightforward concept. So this line is a hyperplane. So this is a flat subspace. We have two dimensions, right? We have x1 and x2, and the line is a 1D subspace within these two dimensions, right? So if you have three dimensions, you can imagine that it would just be like a flat plane, and so on and so forth. And the whole idea, okay, so this looks something like this. Beta 0 plus beta 1 x1 plus beta 2 x2 is 0 in two dimensions. generally in p dimensions looks something like this. And the concept that we'll be thinking about today is in sort of a classification. Can I come up with some kind of rules with which I can separate, where I can separate my two sort of points, two types of outcomes. So in this case, we've got the red points and the blue points, and I'm creating this kind of boundary to separate them. Okay. So we're going to look at different strategies of how to do this. And it'll get sort of, we'll build in complexity as we go on throughout today. So our starting point is something known as the maximal margin classifier. So this is an optimally separating hyperplane. So this is a separating hyperplane that is farthest from training observations. So if we think about a simple example, we're not really going to run into any problems. So this might be x1, x2, with your outcomes looking like this. So the problem that we're faced with is that, yeah, I can draw a hyperplane like this, but I can actually also draw a hyperplane here, or like here, right, or here. So in fact, there are an infinite, I'll just write that out, an infinite number of separating hyperplanes. And therefore, I can do something like this. You can draw a line to your hyperplane. And the whole idea is that you want to maximize this difference. And these distances, these are actually known as support vectors. They look like these pillars that are holding up your hyperplane. And so you're maximizing the sort of perpendicular distance to the point from your hyperplane.
Alan, quick question.
Yes.
Do the distances of like the blue data points and the red data points, they're obviously not all going to be equal because they're, different inherently, but does your hyperplane have to be, I guess, equalizing the distance between both? Like I like, could you explain a little more how you maximize the distance?
Yes, I'm just about to do that.
Okay,
So,
thank you.
maximize M by changing our beta parameters. So such that the sum so you're constrained by this equation. And the whole idea is something like this. Okay, so this equation is essentially going to try and maximize the distance from of each of the points from the hyperplane. If we think conceptually about how this works, it is looking essentially at the squared distance. So that's how it equalizes between what Ashley was asking about. If I move this sort of closer to the x's, you'll be reducing distance to your red x's, but increasing the distance to the blue dots. But because you're doing a square penalty, the trade-off that you're making by getting closer to one side is going to have a bigger sort of penalty. So usually it's kind of like equal on both sides. Hopefully that all makes sense. And there are there's two sort of big issues with the maximum margin classifier. Um, and maybe this will be obvious. Well, the first one is probably the most obvious, non-separable cases. And this is obviously very common. So what is this? X1, X2. This is just the case where there exists no single hyperplane that can separate your outcomes. Right, in this case, there's no line that I can draw through these set of points that will perfectly, or there's no straight line that I can draw through all of these points that will perfectly separate everything. The other issue is slightly more subtle, and that is sensitivity to individual observations. So let me draw two plots. Try to make these identical. Something like this. Okay, and in this case, my line might look something like this, right? Where I want to maximize those distances. Hang on, this one should be a little closer. But if you were to just add even a single point, like right there, then my hyperplane would get shifted down from the original, right? Because of this point here by quite a lot. So even adding, because the fact that you have to do this perfect separation of the points, even adding in a single observation can drastically change your hyperplane. So a more evolved version of this is known as the support vector classifier. So this has general robustness to individual observations. And better classification of most training observations. So this is essentially so this is essentially building off of the previous example, but it's providing a little bit more flexibility. So this is actually the same optimization as your MMC, but with an additional constraint. So this ends up looking something like this, which is the same as before. Except now Rm is multiplied by 1 minus epsilon I, and this is our slack variable. Epsilon I basically is how many points are allowed to violate the margin. And C is the bounds for the number of epsilons. This is our budget for violations. And at C equals 0, it is the same as your MMC. Okay, so the whole idea here, if we simply go back to some of our drawings here, or actually if I even were to go to this one, this helps to deal with both of these cases, because so you can have a support vector classifier that can draw a hyperplane through your set of points, even if it is non-separable, if you have enough of a budget, right? So if I have, for example, C equals 3, I can draw a line like so, because I have a total of 3 violations, and that allows me to still kind of to still separate these. Okay, so this is a way of overcoming some of the shortcomings of your MMC, and in this way, you can also help to address the second issue of the sensitivity to individual observations. If you have kind of enough of a slack, we can say, hey, maybe I like this line here more than this line, and I have a budget to ignore certain points, right? Okay. Any questions about this so far?
I have one question. You said this, but I just want to make sure I heard it right. The distance is calculated by the squared distance from the line?
Yeah, so
Okay.
that looks something like this.
Okay, got it.
Okay, so the last bit is known, or our sort of ultimate evolution of this is known as a support vector machine, an SVM. So this is a super common classifier in the world of machine learning. If we build off of the models we just discussed, right, the maximal marginal classifier and the support vector classifier, this model is analogous to those, except that it doesn't have to be linear. Okay. So if I were thinking about my plot here, you could even, in this case, right, maybe you wouldn't have a great sort of hyperplane. You'd have to do some kind of violation. Maybe it might be like that. Maybe it might look like that. But with a support vector machine, you might think about doing something like this. But in a similar way to our initial discussion about that the hyperplane, I can draw this an infinite number of ways, right? And in fact, one of the big problems is that as you think about your sort of support vectors to your lines, that there are still an infinite number of sort of possible boundaries that can be drawn, even with the same size of your support vectors for any of your points. So we could, we could allow for polynomial expansion for interactions of x's but this explodes in size very quickly. So instead, we modify and generalize computation of the support vector classifier. So our SVC, which was the number 2 model, this uses a linear kernel, but with SVM, we can employ more complex kernels. This can be polynomial or radial. And these are the most common. There are some other things you can do too. And essentially, by introducing these into your sort of optimization, it allows you to have more flexible hyperplanes that don't just have to be linear. And I'm not going to get into the sort of math, the math behind these, but we will show kind of the capabilities of applying an SVM to some real world data. Okay, so let's go ahead and jump on over to R for today.
Alan, I had a question.
Oh yeah, questions first.
Yeah, so I didn't quite follow how did we avoid having many lines, many hyperplanes getting drawn? How did we avoid that in SVM?
Okay, so it's the same. It's the same process. You can think of it as the same process as what we're doing for the line. You can have a single optimization that can minimize maximize the support vectors in your problem in the same way that with the line that you can have, a straight line, you can be flexible with even with a curved line, you can essentially maximize the sort of differences between your line and your support vectors, even if you have sort of infinite flexibility.
And a single optimization can figure out, like, I guess the line is going to be complex, or like in the sense it will be polynomial with a lot of
Yep.
parameters. So, okay.
So you're okay. So essentially, in this optimization, you can do some kind of transformations here, right? And it makes it's going to essentially add more flexibility into the model. It gets somewhat complex in that by adding sort of more dimensions, you have more sort of flexibility to play around with certain things. And so it's not necessarily the case that you always will have sort of identical SVMs depending on the way in which you choose your kernel. Like if it's like if you do radial versus polynomial, because it essentially treats the sort of flexibility in slightly different ways. When the sort of math starts to get pretty complex for for solving the optimization. But if you want more sort of details on how this works, I would check out in the extra reading materials for the class. In the ISLR book, there's a really sort of nice section about support vector machines that will go into a little bit more detail on sort of the mathematics of how this works.
That makes sense. Thanks.
Okay, I'm trying to see, did I? Okay, I did not. So 1 second, I'm adding a necessary file into Canvas right now that we'll need for this. Yeah, so it's under lecture 16 files. So go ahead and grab that if you want to follow along. And let's hop back over to RStudio. Okay. So we'll need a new package, E1071. And let's look at a support vector classifier. So when we do some kind of random draws, you can actually do this function called setSeed. And essentially what that does is you can actually choose the way that a random draw happens is based off of some kind of like seed value. And if you use setSeed, you could essentially choose what that is. So if we do this, then all of the random draws can essentially be non-random. They're sort of deterministic based off of the seed. So if everyone does this, whatever random draws that we do should technically all be the same. So what we see here is that we're generating a matrix of x's, and the entry values. So I should have 20 rows and 2 columns, I think, of randomly generated values. And these values, even though we did this R norm random draw, should actually be the same for everybody because of the set seed. We're going to make some Y's as well. It will look something like this. So all we're doing here is we're making our x1s and x2s, and then we are assigning points as essentially red or blue for our y's, -1 and 1. And I'm creating, oops, I should be doing this up here. I've done some assignment here. And we should see what this looks like. Plot of x, color equals y plus 3, usage. Okay, so I have some points here, similar to our example, right? And we have blue and red points that look something like this. We're going to put this all into a table. So we have our x1, x2, and our y that looks like this. Okay, so let's go ahead and put this into SVM. And importantly here, so the support vector classifier is just a subset type of SVM. So the syntax is pretty much analogous to the types of things that we've seen so far. So you're going to be doing Y on everything else. That's the period coming from data. And in this case, we're going to do the SVC, support vector classifier, which is just a support vector machine with a linear kernel. I'm going to set the cost equal to 10. So that is our budget for how many points are allowed to violate the line. And scale equals false. Okay, so what's the scaling? So recall that our support vector distances to the hyperplane are based off of Euclidean distances to the line, and therefore, if you choose not to scale, if the values of your x1 and your values of your x2 are like really different, like if x1 goes from like 0.1 to 0.3 and your x2 goes from like 1,000 to 3,000, right? You can imagine that the hyperplane getting drawn will be much more influenced by x2. In this case, the scaling doesn't matter because they're both getting drawn from this R norm with the same parameters, and so the range of values is pretty similar, right? So in x1 it's -1 to somewhere above 2, and similar here, it's like -0.5 to around 2. So scale equals false in this case. Go ahead and run that and look at the summary. It's not going to tell you much, right? So one of the things to keep in mind here is that what other sort of classifier models have we talked about? The sort of main big one, right, was the logistic regression, where you have your discrete values for y being described by your x's. And in that case, there is some kind of interpretability to your x's. But in this case, we care much more about just saying, are the points on one side of the line red or are they blue? And you're not really describing sort of the relationship of variables to a specific outcome. You just want to be able to predict the outcome. So in this case, our summary is going to tell us some attributes and parameters about the model, but it's not going to have the same sort of descriptive stuff that you're getting through like betas, for example, through the betas in your logistic regression. But we do a plot of this. We can see this. So this is a line getting drawn like this, like so. You have a little, there's this little kink that's just a product of the kernel approximation of your line. And in this case, so we gave it this budget of 10 violations. And so it does that. So 1, 2, 3, 4, 5, 6. And I think there's some circles here. Oh, no, that's actually on the right side. Wait a minute. Oh, sorry. The X's are the violations on both sides, and then it's by color. Okay, so you can see 1, 2, 3, 4, 5, 6 violations total, and then this line otherwise would describe your SVC that maximizes the distance to the points on both sides. And basically, this hyperplane line is going to allow us to make this general classification for any future set of points. Everything on this side will be one classifier or -1, and the other one will be +1 on this side. The two possible Y outcomes. Okay, any questions about that? So now we'll look at an example of this, of the nonlinear version. here I'm actually going to load in some of the data. Oops. That is on Canvas. So we can see okay. I'm doing this kind of for simplicity. So names tells me the object names in ESL mixture. And what I'm going to do is I just want to attach all of those to my working space. So it's going to create a bunch of variables x, y, x new, prob, marginal as just objects that I can work with. But first I'm going to remove the x and y's that we had defined sort of up here before I do that. So now when I do this, we can see that I can call my x's and my y's that were defined via my ESL mixture data. So now these are different from what they were before. And we can see what the x's and y's look like. Like so. Okay, so we have a much more sort of complex set of points. This would be sort of really difficult, right? So first of all, in the maximum marginal classifier, you have all the intermingling of points. There are no hyperplanes that can kind of draw this. And I think this helps. So if you think about the real power of the support vector classifier and machines is that now we can see a case where there's much more intermingling, right? And so I don't know if the best strategy is to draw like a horizontal line or some kind of diagonal line this way or a line this way, right? But by using the SVC and SVM, it can figure that out sort of for you in particular for these examples that rapidly become difficult to visualize sort of manually, right? Like all the examples that I had shown before, you could reasonably figure out good lines or hyperplanes to draw. But in this case, it's a lot more challenging. So we'll do the same thing for a data frame, actually data table, not data frame. This time we're going to create a SVM with a radial kernel. Y. So same as before, except this time our kernel will be radial. And here we can enforce some kind of cost. So cost I'm going to have as 5. We'll run this, take a look at the summary. Okay. And I should mention this cost value is our C, but this is a relative budget now. It's not like an absolute number. And you can play around with this parameter to see sort of how flexible you are allowed to make it. So in this case, we can see how it's drawn our sort of classifier, and we can see the violations in X's. And you can mess around with your cost to see how well it does. So you can see looks something like this if I increase the cost, or if you decrease it. And the cost parameter is essentially your way of tuning, well, both the kernel and the cost are ways that you can help to tune the way that the SVM is drawn. And so you can probably see where I'm getting at here. The best way to choose your cost value is, again, by doing out of sample sort of testing and arriving at a point where you have sort of the least classification error as possible when you sort of take points out and introduce them into this sort of classification. Are they being classified the right way? And so the cost, similar to all the rest of the tuning and scaling parameters that we've done, can be selected in this way. Okay, any questions about SVMs? Okay, can I give an example of what X1, X2, and Y could be in the real world? Yeah, let's see. Off the top of my head, I'm trying to think of some of the examples that we've done before, right? This is the same thing as any sort of like binary sort of logistic regression. You could do something like I think our first example in logistic was thinking about like election outcomes. You could think about like how demographics might pertain to or result in a particular outcome. So does the combination of education and income, can that relate to whether or not a like a census tract votes a certain way in an election, right? So if they're like, if you get a Democrat winning or a Republican winning, and then you could have on your X1 and on your X2, this could be like your income and level of like education or something like that. So basically, the application of the SVM is going to be to a regression, a classifier regression, right, where your Y has some kind of distinct outcome variable. It's discrete as opposed to being continuous. And then you can apply this kind of technique to do predictions based off of your x's. You can do more than just 2 dimensions. You can have x3 and x4. It's just that I can't visualize that really once you're going beyond 2 dimensions. But it can still provide prediction. It can still provide prediction outcomes as you plug in new x1, x2, x3s, and so on. Okay, I see another question. Is there a way we can quantitatively assess the quality of a classifier? Yeah, exactly. So how would we think about assessing quality, right? So if these classifiers, if their main if the main use of a classifier is being able to predict an outcome, right? So that's like if I were to introduce a whole new set of points, like something over here, something over here, something over here, something over here, would I be able to apply this SVM to accurately classify that point? And so the quantitative assessment of how good a classifier is would essentially be how well does it predict. And we know how to do that, right? We can have testing sets where we apply it to sets of where we apply a model to it, such as an SVM, and get a sense of how well it would be able to predict a particular outcome. So yeah, so you can definitely quantitatively assess this using cross-validation measures. Any other question? Okay. Okay, I see a question. Can I repeat when to use the set seed function and how to decide the number? So set seed is just is whenever you want to is whenever you want to make it so that your random draws are kind of a fixed value. And so this is the times when I would do this, or any time when I want to like make sure that I'm getting the same sets of values out of my random draws. So if I do this, set seed, and I want to do 10 random draws, you'll see the numbers that are set over here. And the next time I do it, it's going to be random again. But if I set seed 100 here, I run this again, we'll notice that the points after any time I set the seed will be identical. So -0.502195 is the same value here, and it's the same for all the draws here. So anytime you want the randomness to be controlled, if you're like doing some kind of example or something, or if you want to make sure like 2 different things are aligning, this is an easy way to do that. And the value inside the set seed, the like 100, it doesn't really matter. It's just, you can choose any sort of seed, and as long as that number is consistent, then the random draw will be the same. So up here, I think I just picked a random number. But if everyone uses this number in the set seed, then all of your draws will be the same for the next random draw that you do.
I was wondering, like the example you gave about the election, and when would you do a logistic regression versus a classification?
Yeah. So the nice thing about the logistic regression is that you get, in the logistic regression, I get these like beta values, right? So let me, one sec. So in a logistic, you end up with like beta 1 equals, I don't know, 0.5, beta 2 equals negative 0.01, right? And then remember, we can use this to translate into some kind of probability space where we say as X changes, the probability of outcome Y, K looks something like this, right? And we might go from like 0 to 1. So what I will say is that the nice thing about the logistic regression is that I can tell you, hey, as age goes up, for example, the probability of like a particular like election outcome changes in this sort of way. So I can have some kind of interpretive I can interpret the influence of my X's on my Y's. Okay. And the sort of the simplicity of the logistic regression allows me to have this ability to interpret the relationships, the direct relationships between my X's and my Y's in this way. This is sort of analogous to this whole idea of like, oh, when would we use like a linear regression versus using a splines, right? If you recall, the sort of drawback, let me pull up this slide if I can find it. So if you remember, the drawback of the logistic regression and that sort of thing is that the boundaries that it draws has to be sort of linear. But in having that constraint, it allows us to interpret the relationships a little bit in a more straightforward way. The SVM doesn't really let us do that. It doesn't give us the ability to do the interpretation that a logistic regression would provide. And if you imagine, okay, the plot that I just drew that had these lines, that's analogous to our linear regression versus like our splines, right? And in the splines, you don't really have anything to interpret, but you can make these predictions. So SVMs are almost always, well, pretty much always going to give you better predictions than a logistic regression, right? Because at the very least, the SVM classifier could draw the same straight lines as the logistic regression at the worst, but at best, it could do some complex things such as this. So then it really comes down to the context of whether you are trying to do to make like causal inferences or understand relationships between X's and Y's, which you would then try and do like logistic or LDA or some type of regression like that, versus if I just care about prediction. And if you just care about prediction, which is sort of much more in the sort of machine learning school of thought, then you would just do like some kind of SVM classifier. Does that make sense?
That totally makes sense. Yeah. So it's in some way it's similar to KNN. I'm just trying to think back all the methods.
Yeah, exactly. So SVM is an alternative, like non-parametric approach to classification that KNN would be doing. You can, it's like, it is like KNN and SVM are two types of models that are focused in the predictive side of things. And then this goes back to Mohammed's question. Is one classifier necessarily better than the other? It depends on the context of the problem. And you could do both in KNN and in SVM. And then in some cases, the KNN might do better. In some cases, the SVM might do better. I think generally SVM is a more preferred classifier for certain reasons. I don't actually know. Practically speaking, it's probably having to do with issues of like complexity and how it addresses sort of like multiple variables. But I think SVMs are generally done a little bit more than KNNs. I think it's actually, if I recall, I think it's a lot easier to overfit with KNNs than it is with an SVM. Okay. Any other questions? Okay. So why don't we actually end here for today? I don't want to start jumping into neural networks. I think we'll quickly run out of time, but we'll start that next lecture. Yeah, okay, so we'll end here for today.